chapter 4 is really starting our organic chemistry reactions for the year. It's chemical reactions and radical halogenation. So as we get started here, there's some definitions that we need to understand and some terms that we're going to be using as we go through the subsequent chapters that involve mechanisms. So what is a mechanism? It's a change that occurs as a reaction goes from reactants to products. So often in GChem, we have on one side our reactants, right? And then over here, we have our products. And we're just concerned with the overall snapshot of what happened. And in OChem, we call that the observed reaction. Right? It's the big picture reaction. But in organic chemistry, we're interested in these little steps of the mechanism, which are called elementary reactions. They're individual reaction steps that occur as part of that mechanism. Sometimes we call them mechanistic steps also, and sometimes we simply just call them steps. Now, in elementary reactions, the intermediates are reactants or products in these elementary reactions, but they don't appear in the observed reaction though. Typically, they're unstable, and they usually can't be isolated and stored. So kind of putting all of this together, if we look down below, here's the idea. Here's a mechanism. Okay, so we're not going to put even chemicals in here. Step one of the mechanism would be reactant A going to intermediate B. All right, now, the second step would take intermediate B and then finally convert it to the final product C. So then the observed reaction would just be A going to C, with B here being your intermediate. And step 1 and 2 we would describe as being mechanistic steps, or elementary reactions. Okay. Now before we get into the actual mechanism of a free radical reaction, we need to review some thermodynamics and kinetics, mostly kind of general chemistry stuff. So some of the stuff you've seen before, and you may have forgotten it a little bit, and we might want you to think about it a little bit differently in organic. So let's talk about it. So the first thing that I want to look at here is free energy change. So we're going to use this relationship delta G and KEQ when we go through and try to determine where equilibrium lies in certain reactions as we go through the semester. But remember, it's equal to negative RT ln of KQ, or 1.36 log of KQ in kcals per mole, where R here is this number, T is our temperature in Kelvin, and that little naught sign up here is your standard state. That's 1 atmosphere at 298 K. Now, the free energy depends on a couple of things. Number one, your delta H, that's your enthalpy. Okay. And your delta S, which is your entropy. So we'll take a look at those in just a second, but the overall expression is delta G equals delta H minus T delta S. And I wanted to give you guys a little table here. So here is our delta G value, right? So here's our delta G, and here is the K value that you would get from calculating that delta G and incorporating it into the formula that we see over here on the left-hand side. So a delta G of 1 gives us a KQ of about 0.184. That gives us about 15.54% products there. So as we go down to 0.5 here, you get about 30. Right, 0 takes you to 50. Right, and so on and so forth. But I want to show you right around this number here, right around 3, we get about 99%. So it's a good thing to remember that if your delta G is more negative than about 3, right, kcals per mole, then the reaction will go to about 99%. This is useful in biochemistry because a lot of the steps, for example, in metabolism, delta G's have been calculated, so you can go through and you can see if is that a favorable reaction or not. We can also use these delta G's if we go back and look at the energy that's required to do conformational rotations. For example, like in butane, we can calculate the percent that we'd be in anti versus gauche or something like that. We could do it for our chairs also, right, in determining which chair is more stable. So this next section is going to deal with kinetics. So remember that the rate law must be determined experimentally. A is the order with respect to A, B, so on and so forth. And the overall order is equal to A plus B. Now the value of that K value depends on temperature, is given by this Arrhenius equation. So our K value here is equal to A, which is our frequency of collision, right, times E raised to the negative EA. Remember, EA stands for activation energy, divided by R and RT, which is temperature. Okay. So EA, if you recall, that's the minimum energy required to reach the transition state. So if you look at a reaction, and we're going to look at this on the next page a little bit more, but if we were to start off over here and have our reactants on this side, right, a familiar diagram might look something like this, where here's our energy, here's the reaction coordinate, right, and this is our starting energy. So this little hump that we have to climb over here, that is your activation energy, and this at the top is your transition state. Now, if you remember from GChem, this process that I'm showing here would be an exothermic step. Now, we'll look at this in more detail just on the next page. Now, notice that temperature is in here. So the way that you can help this reaction proceed faster is we can lower the activation energy. So if we could get that number to come lower, like something like this, that would help. And then the other thing is if we increase the temperature. So the idea is that at a higher temperature, the molecules are moving faster. They have more kinetic energy. And with that extra kinetic energy, they have more potential to overcome the barrier to reaction, which is your activation energy, because there's more energy stored in them. So remember two things, that temperature is going to be important. And then the other thing, of course, is the activation energy. So more temperature, molecules can move faster, right? Reaction rate increases. So here, if we look at this reaction down here below, temperature and reaction rate. So here is methane plus some type of a halogen radical, and that's going to give us a hydrohalic acid and CH3, a methyl radical. And here we have different halogens, activation energy for that step, and then the rate at 300 K, right, versus 500 K. And you can see down the line, right, all of these have an increase. So 140,000 to 313 to 18, right, so on and so forth. So we can see the reaction increases as we increase our temperature. And then we mentioned before, EA is going to play a role in this. So your activation energy. So here are some activation energies for various processes. So ethane, the rotational barrier, cyclohexane, ring flip, right? And then just some general numbers, 20, 25, 65. That's about the amount of energy required for a pi bond rotation. Now, pi bonds can't freely rotate, so that means we have to break it and then reform, right? So that's the energy required to do that. Here's our K value. And if you take 1 over the K value, you can get some time. So, right, for ethane, that's about 16 picoseconds. Cyclohexane ring flip, 12 microseconds. You got 47 seconds, 2.5 days, and the pi bond rotation, I'll let you guys calculate that on your own. That's a long time. So it just doesn't freely happen at room temperature. So you'd have to increase that temperature quite a bit to get that rotation to occur. Now, this is a nice little diagram here showing the energy of reactions. It's what we kind of drew on the last page here. So here's the process for an endothermic reaction. Remember over here, we're starting off with our reactants, right? And we're coming over here to our products or intermediate, right? Now the reactant could also be an intermediate also. Now, for this, an endothermic reaction, there's going to be energy that's absorbed here. So that represents the amount of energy that's absorbed, right? That's your delta H. That delta H is a close approximation to your delta G also. Here for an exothermic reaction, again, here's our reactants or intermediates. Here's our product or intermediate of an elementary step, right? Here we have our activation energy in our transition state. Right, so what we're doing is we're coming up here to our transition state. Then we're coming down here to C plus D, which would be our product or the next intermediate. Now this amount of energy here is the energy that's being released. So we simply will make a note of that. That's the energy released. So, in general cases, things will get hot because you have an exothermic reaction, right? That's kind of the idea there. All right, now, last thing to point out here before we move on to this next little section is that delta G is the change in free energy of the reaction. It's the difference in energy between the products and the reactants. So that delta G is often a close approximation to delta H. This is often true if the T delta S term isn't a huge factor. So sometimes we just make that assumption and we just move forward and it's good enough for us. Other times it's important to be very quantitative and we might include the T delta S term in there. And as we said before, that activation energy, that is the difference in energy between the reactants and the transition state. Now, the reaction step with the highest activation energy will be the slowest, and therefore the rate determining for the entire reaction. So one of the things you see as we go through OChem is reaction mechanisms are more than one step. So we might start off here and come up and pop off here and then come down and down, something like this. Right? So in this step, that's activation energy number 1, right? And then hard to fit that in, but that's your activation energy for step 2. So here's your number 1, here's your number 2. So the RDS on this would be step number 1 because it has the higher activation energy. Now, there are some things that can lower your activation energy. And if you remember this, especially in like biology, something that's talked about, enzymes will do this. An enzyme's job basically is to grab a hold of reactants, put them together, right, so that they can react in a more efficient way. And then in OChem, we see these acting as catalysts, right? So we don't necessarily use enzymes for reactions, but we might add, iron tribromide to help facilitate a reaction in a benzene ring or something like that. Now, the other thing that I'll mention here, and we're just going to make a note of this, and then we're going to look at this as we get kind of through this reaction chapter a little bit, but there's this very important postulate called the Hammond postulate. And it simply states the following, and this is key. It states that the related species that are close in energy are also close in structure. So what that means is this, and this is where it's like the key thing. The transition state structure for an endothermic reaction looks like the products. Okay, and the transition state structure for exo looks like the reactants. So if we look up here at the top, the endothermic reaction, we can see here our transition state is a little bit closer in this case to our products, our intermediates, and here a little bit closer to our reactants here. Now the bigger that delta G / delta H is here, the more pronounced that difference becomes.